The next speaker is Andrea Martin. She did her work at the School of Philosophy, Psychology and Language Sciences at the University of Edinburgh, and also at the Max Planck Institute for Psycholinguistics in Nijmegen. And she will speak about linking linguistic and cortical computation via hierarchy and time.
So I'm going to continue the love song to Nye's data, or the power ballad, if you will, that this afternoon session has been, but from a different perspective. So it's late enough in the afternoon that we can agree that one of the common desideratums across the brain sciences and cognitive science is relating these computations that we think the brain might be carrying out to the measurement or readout that we can get from, in some cases, a badly drawn caricature of the brain and its signal. But nonetheless, obviously this is a cartoon, both of the computation and the signal. But the argument holds that we might be able to take cases where the input to the system, right, and the output, or our perception or our experience, differ in systematic ways, and we can use that difference to infer the kind of computation that the brain might be carrying out to get us from that input to the output, right, our experience or perception. Now, a particularly hard version of this inferential problem comes from perceiving language and speech, as we all know. Right? So Nye has told us about this recently, so I'll save you all the going through it again. But I do want to make the point, since we've all been worrying a lot about the isochrony, I don't think that the isochrony is such a big problem, for better or for worse, because I think that mechanism, whatever is generating from the isochronous speech or from this 4 Hz signal, in the end, a hierarchical sentence representation, right? In the isochronous case, it has to be somehow derivative from the same mechanism that's working in the non-isochronous case, right, in everyday speech. So what we might want then is a way that we can account both for the products of the computation and the readout that we get, right? And it would be great if once we knew the computation, then we could then use that to do even more inference and start talking about mechanism. So the idea here is that I want to get to a candidate mechanism that can get us both the products of computation, so something that goes from a sequence to a hierarchy, right? Maybe first beginning not with all the specifics of natural language, but the point is that it goes from a sequence to a hierarchy, while expending energy in a cortical-like way. Right? So I'm going to present some simulations in a model today of Nye's data. And I just want to be clear that this is a model, and by definition, it's just an existence proof, right? So we're restricted to the vagaries of inductive inference here. All we can say is that this is one way that the brain could solve the computational problem, right? So that means that this model is not a cortical microcircuit model, certainly not a parser, and I'll talk later about why I think that that's maybe not actually the goal that we want to get to. We maybe don't want to use natural language processing parsers as our cognitive processing model. It is a model of information representation and processing. So it's a way to think about it is that it's an existence proof of how you can represent information in a neural network system and how you can process that information in real time to get from a sequence to a hierarchy. Another way to think about it, to try to make more contact with the world of oscillations, is you can think of it as a model of aggregate unit activity, or as assembly or functional assembly activity. All right, so before we think about how we might model oscillations, it's important to think, okay, what's the end goal? What's the product that we want to model? And that's language. So we need to keep in mind the computational requirements of language, which are actually quite hard and differ from the rest of the perception action systems, I would argue. So first we need discrete units. That seems trivial, but when you're using statistical learning and in connection systems, that's not trivial, and I'll get to why later in the talk. Worse, I'm going to argue that we need symbolic units, and that's actually a hard computational problem. But it's not hopeless. We also need decompositionality, right? So this is the knowledge that you have when you understand the sentence or the phrase, the fervently crying children, right? You don't lose the knowledge, or you don't lose the information that you have about the subparts, right? The fact that fervently, right, is a word that is an adverb that's derived from an adjective, and you know that because you can put "ly" on it, right? While crying is an adjective derived from a verb. But people don't say, or they don't produce, the fervent cryingly children, for example, right? So there's some knowledge there about how you can put these things together, and you need that in a system, and you need to be able to go both ways, right? So you need to be able to go compose them together and not lose that information when you do, right? Okay, so these are the goals for our system so far. And lastly, we need something that makes the system productive or generative. And usually this is explicated as a case of recursion or embedding, where you can have an infinite sentence or embed as much as you want. But I think it's actually, in this case, for neural network models, important to think about it as a case of understanding things that we've never heard before and saying things that we've never heard before, right? And this again links back to the idea that there's symbolic units that we need to represent. Right. So, it sounds like a tall order already. What do we do? Well, if we look at these cases, these requirements, these principles, I want to argue that the one thing that sort of ties them all together is they all have an element of relationality. So in each case, you have some representation that you have to relate to another, right? And so then what do we know about relating things together, and what might we know about that relating things together in a neural system? Okay, so now we get to the beginning of the harder problems. So how do we relate things, right? So one way that we can relate things, so if the task of the system, of the computation, is just to relate the pairs 1, 1, 2, 2, 3, 3 on, for example, the x and y axis, one way to do that is to just form associations. And this is what the bulk of connectionist models do, or any associationist system that creates a mapping. So within a restricted domain, that restricted domain is the data it's seen, the data it's been trained on. It can learn very well, right, that 1 goes with 1, 2 goes with 2, 3 goes with 3, 4 goes with 4, for whatever it's seen, right? Another way to relate things in a system is to generate a function or a symbol, right? And there are benefits to these and drawbacks, and we'll talk about both of those. So again, the restricted domain aspect actually might seem like it's not that big of a problem, but actually if we want a model that can do all the things that we want, it becomes one. And we don't see that so much because we're now, with a lot of computing power, able to fit lots of data. So in the unrestricted domain case, so with universal generalization, there are different problems that we can solve with this. So for example, if you had a system that learned 1 goes with 1, 2 goes with 2, etc., if you were to give it the number 36, it would not be able to give you 36 back, right? Because it's never seen 36 before, right? So it only learned the mapping 1 to 1, 2 to 2, 3 to 3. So if you give it a different starting value, it will fail. But if you represent that same relationship with something like f of x equals x, you can give it anything, and it will give you that value back. And that's the generativity that we need in the system. Another way to see the problem is that if you gave it a slightly related operation, so you have some operation in the system, and you just want to augment it slightly, right? And in a lot of systems, as soon as you have a new data set, you need a new model, right? So if you train a network on one data set, it's not going to generalize to another, even in the most fancy cases, and I'll get to that in a second. But if you had a system that could represent this, you can generalize to new input. So these problems and benefits link up to two major distinctions in the modeling world, right? And that's in the traditional world of connectionism versus representing information in a symbolic system, right? And I'm going to argue that we actually need elements of both. And so the most modern equivalent. So all the things that I'm saying now I'll talk about as connectionism, but it does apply in the same way to deep learning systems. And all of the problems with symbolic systems that don't learn, I'm really talking about Bayesian models, but not wanting to be too controversial. All right, so where does this get us? That means that we want to have a hybrid. We want to have the benefits of a connectionist system, so something that can learn, but we need the representational power of a symbolic system. So we need to be able to get from feature-based whole object representations to symbols or component parts that we can put together. So the learning I'll talk about in the second part of the talk. But the startling thing about this is I'm going to use a model that actually was developed to do something completely different. And this is appealing because it, on the broadest sense, allows us to think that maybe some of the things that allow us to understand language and speech are borrowed from other systems or repurposed. So the model that I'm going to present to you is called Discovery of Relations by Analogy, and that's because it was developed to model human behavior through development of analogy. So that's something like this case here. So this is a bit pixelated, but here we've got an ascending size of circles here, and the task is to say which of these two examples is like the one on top. And even though it's pixelated, I think you can still get the message. And so if you're human, and also not a machine or not another non-human primate, you can see that there's something the same about these cases, right? That there's an ascending order that's not the same here, right? So that's an abstract notion of same that's not derived only from the perceptual input. Here it gets a bit even harder. and these are the kinds of things that the model solves. We can go again from ascending from small to big, but now in another domain. So now we're using darkness or pigmentation or however you want to think of it to signal that, right? So here, the thing that's same about these is that there's an ascending intensity. So this is a symbolic-connectionist model that was built to be able to answer these kind of questions or do these kind of tasks the way humans do. And another inference that it can solve as a way to sort of get you more familiar with the kinds of problems that relational processing buys us apart from language, and whether it solves language for us is up for debate, but is this inference. So if you know that John loves Mary, and you know that Mary loves Sue, and you know that Sue loves John, who is Mary jealous of? No? You're all human, I know it. John, thank you. Right, so to get a neural network system to solve this problem, right, it turns out you're gonna need symbols or a predicate logic to do it. Okay, so that's all great, sounds kind of unrelated to language. Well, let's get back to how this relationality relates to what we might want to do when going from a sequence to a hierarchy, right? So this is not the first time. So there have been earlier attempts to realize a symbolic system in a neural network, and that worked fine as long as you hard-coded it, right? You had to hard-code the symbolic representations into the neural network. Now, maybe that's interesting on some level, but it doesn't quite get us all the way there. So this model actually learns to symbolize representations from distributed representations that we can get more easily in classical connectionist networks. And I'll talk about how at the end of the talk. Okay, so this model also has simulated lots, like I said, of these developmental tasks. So not only does it do the task on human-level performance, but it manages to do so across the trajectory of development. So it can match through training the behavior of 2-year-olds, 3-year-olds, 4-year-olds, et cetera, to adulthood. Okay. So now what makes it special? Why is it worth using? So it has all of the same assumptions that recurrent neural networks or other connectionist networks have, apart from a few things. Right? So these are the key things that I think are doing some of the hard computational work, actually, and they're very simple conceptually. So the fact that the model defines separate banks of units that it can compare activation across, so you can think of this as like different functional networks that can then talk to each other, this is going to give it some of its power to generalize later, you'll see. And also, crucially, it uses time to carry information. So most neural networks don't use time to differentiate inputs, right? You have to do lots of the footwork in how you structure the stimuli, but this network uses the fact that stimuli occur at different times to keep them separate and put them together as needed, right? And in order to do that, it has lateral inhibition and integration at different time scales, and that is slightly different from normal, your sort of bog standard connectionist model. All right, so back to why we're doing any of this. So we took the English text translation of Nye's stimuli in vector form, so it was quite literally the text in brackets. And we were going to train Dora on this, but then also train a recurrent neural network, which I'll talk about in the next slide, in order to ask the question, is it something about how information is going to be represented in Dora, that is, across layers and using time to connect it and disconnect it, that gives rise to the signal that we absorb from cortical oscillations? Or is something, for example, like the seriality of presentation sufficient? So just presenting the stimuli every 250 milliseconds, is that enough to give you the pattern, right? So that's a way for us to then say, okay, is this, through inductive inference, a candidate mechanism? And also to rule out another account for how we might get the signal and the output. All right. So then we took versions like this, so fun games waste time, one of my favorite of the stimuli, and then a word list, right, so all nouns, and then we made what we call Jabberwocky, which is, not the most traditional sense of it, by just preserving the syntactic category of the words in the sentence, but putting them together in ways that were not that are not composable and that the model had not seen before. And then we just took the noun phrases from the grammatical conditions and put them through. And then in both cases, so for Dora and for the recurrent neural network, we just gave each word every 250 milliseconds, like in the human experiment. And we trained the models on the grammatical stimuli beforehand, and we gave each model the same input. So it gets a signal that's the beginning of the trial and a signal that's the end. And that sounds mysterious now, but in the second half I'll talk more explicitly about the learning. And again, just to contrast here what's going on, So you can think of these models this way. So this one creates a hierarchy from a sequence in a layered neural network, and this just has one hidden layer, right? So here it takes an input, it adjusts itself as needed to give the required output, right? Okay. Right. So in both cases, I just want to give you a sense of what representations are like that the networks are processing. In both cases, the networks start with distributed patterns of activation. So they take some feature vector, right? So this is in text, and it converts it into whatever text form it wants, right? And then, so ASCII or whatnot, and then it represents that in a space of distributed nodes. That's the same in both model cases. And in this model, then, the hidden layer just adjusts itself in order to get the right output. So that's to say, it learns the sentence. And the key thing here, before I show you the results of the activations in the network, which is our dependent measure, is that the recurrent neural network learned the sentences with perfect accuracy. So that means for any given x, it can tell you the next n words, right? So it's not that it doesn't learn the sentences in the it learns the sentences. It just represents them in a completely different way than it seems like the human system does, not to foreshadow too much. All right, so this is the kind of representations we have in the recurrent neural network, so a distributed representation in vector space of this. In Dora, however, we represent things slightly differently. So here, I've visually represented this as a predicate, which it is in the neural network space. But here's where the distributed vector representations come in. And then, at the onset of the word fun here, the network, after learning, will fire all of the structure it knows that's associated with fun, right? In this case, it learned, right, that fun is the kind of word that can start a sentence, right? So as soon as it sees fun, it activates structure related to these things. And here, this is because the model represents one-place and two-place predicates. So because it knows that fun is a one-place predicate, right, on the onset of games, it keeps the next level of node, and this is a conjunctive coding node, that represents both fun and games. So here, this is the key difference. So by doing this across layers, this network can keep fun and games separate, so it doesn't lose that information, while also representing the conjunctive code for fun games. Now, in the recurrent system, we'll see there's the whole sentence is one vector together, right? Now, here's another step of inference. To represent something like a sentence or a proposition, we use two-place predicates. In that case, at the onset of waste, right, we actually split waste into two roles, because it's a transitive verb. So the onset of waste, there's actually two nodes that fire slightly in asynchrony, and that's to signify that this is the waster role, and that's the thing that's being wasted. And then at the onset of time, this stays on. But you should see, with some foreshadowing, that there's something important about the fact that information is represented here on different timescales and different layers, and that they stay on for different timelines. All right, so back to the stimuli. Again, we're going to, now what our dependent measure is to then observe the activity in the neural networks. So what we find, here we have the activation in the driver of Dora in the buffer, which I'll show you later in the architecture, that closely follows the human cortical signal, right? And that comes directly from how we're representing information in the network. If you look at the recurrent neural network, here we've just taken the activity of the hidden layer for the same stimuli, the grammatical condition, right? We see some activation at 4 hertz, but it's only for about 10% of the units in the hidden layer, so that's not very many, right? I don't know, is that an oscillation? Yeah, so that's a striking difference, right? So that, remember, the neural network here solves the problem as well. So both networks can tell you the output with 100% accuracy. It's just that they're solving the problems in different ways. All right, so I mentioned the Jabberwocky condition. And so here you'll see that the Jabberwocky condition spikes just like the grammatical one. And it's maybe difficult to see, but the phrase condition gives us something at 2 hertz and 4 hertz, but not at 1 hertz. And the word list gives us only something at 4 hertz, right? Now, the Jabberwocky condition we were interested in because we wanted to see, okay, has the model generalized something that's syntactic, maybe? I think that's still a step too far to go. But in order to evaluate this, we looked at the long-term memory of the model, which is separate. And there is a difference here. So these plots are kind of weird to read, but these are snapshots of activation across the long-term memory of the network after every 10 cycles. And here, for the grammatical conditions, you see that you can think of the activation as being more peaked. So it's more concentrated on predicate-argument combinations that it knows or has seen before. In the Jabberwocky case, it's oscillating in the same way, so it's binding the information together in the same way, but the activation in memory is more distributed because it's making contact with arguments and predicate structures that were combined in other ways previously. So we thought this is a nice way to illustrate that while the model oscillates like the grammatical condition, it does differentiate between grammatical and Jabberwocky stimuli. And so these are the same conditions in the recurrent network, and we see the same thing. So a modulation at 4 hertz, but again, the highest percentage is 15% of the units, or maybe 17% in the hidden layer, and maybe something at 3% at 2 hertz, but it's not solving the problem in the same way. And I think that's clear from this illustration. So where have we gotten so far? We've gotten from a sequence, not speech-like, but a linear sequence, to a hierarchy, and we've expended energy in arguably a similar way as the cortical signal did. Now, just to sort of illustrate that with this admittedly funky PowerPoint and animation, here's what it looks like again. So at the moment of fun, we activate all the structure we know about fun. We keep some of it on for games because we want to conjunctively code fun and games and compose them into a larger unit. Then at the onset of waste, we do that 2 times. We split that over the 2-role predicate, and then we get our concomitant pattern of energy expenditure. All right. So we call this mechanism on a broad layer across the network time-based binding. And what it really is doing, it's using time to encode hierarchical relationships. And you can think of this as a form of desynchronization between layers, actually, right? Because what you're doing to keep the words and the phrases separate is desynchronizing them in time, right? So keeping the phrase on while the word goes off. And just that very simple concept has given us hierarchy from a sequence and oscillations that are arguably human-like. Right? Just to say it in a different way, it's the processing of the representations in this system that generates the oscillations, right? So oscillations across the layers, across the whole network, got you hierarchy from a sequence and preserved decompositionality. So where does this leave us? So if we go back to the 2 systems distinction here, it's important to remember that, so it's great we showed that the symbolic system can give us these oscillations, but we want to be able to learn that. Otherwise, it's not really facing the hard problem, right? So the benefits of connectionist systems is that we can use them to learn from experience, to learn from the environment, and that's a really important ability, right? But it doesn't seem to get us symbols on its own. So the sort of dominant symbol systems, they all have modular supplied representations. They get rules specified to them or graph grammars given to them that contain all the information they need to fit any data set, right? They're Turing complete. So how can we go then from a system that can learn from experience to a system that can learn structured representations from experience, right? And this is, again, not a new idea. So there's lots of great arguments for why connectionism is not enough for thinking and reasoning from my collaborator Alex and his advisor, and then also in language from Marcus and Thinker and Prince. So this is an old, hard problem. And how it's been solved typically is to either ignore structure, so that's traditional connectionism, assume the structure, and then the third option is what we're going to try to do, and Alex has done, and we're going to try to move forward, is to learn structured representations from unstructured input. So what this model is an algorithmic account of how structured symbolic representations can be learned, right, from stuff that's unstructured. Now, I've talked about this through the whole talk, and this is really a crucial part. So the model, I said, assumes different banks, and this is really one of the key parts. So it has an input layer, these features, right? And then it has immediately one bank of units and then another. And we call them the driver and recipient, but really you can think of them as one processing moment and the next. Or you can think of them as the focus of attention and the stuff that's just been shunted out of it. And then the model also has a long-term memory. And this is the base architecture that we assume. And then after learning, which is fueled by the same time-based binding as we do processing, we can generate these predicate structures, right, in both spaces. And so another way to try to explain this process that's hopefully more accessible is if we want to learn something, we need to compare 2 things together, right? So here, one way to learn invariance is to take any 2 things in your environment that you might come across and compare them. So imagine you have an apple and a fire engine, right? So you step outside, you see a fire engine, and then you see an apple on the ground, or however. Now, there are going to be lots of things that an apple and a fire engine don't have in common, but there are going to be some things that they do have in common. And those things are going to get twice as much activation in the feature space, right? So for example, that they're both red and shiny, right? Both apple and fire engine are going to be passing activation to redness and shininess in a feature space, right? And if you compare those two objects together, you can, through intersection discovery, tap into that invariance, right? So through comparison, you both inherently get the stuff that's different and the stuff that's the same. Sorry, so here's the two things that are getting twice as much activation because they're getting mapping from both the apple and the fire engine. And in a previous version of the model, this was just assumed, but now we found a way to actually compute this using either entropy reduction or free energy, and it's just, again, from the concept that things that are the same are going to pass the same activation upward, and things that are different won't, right? So another way to think about this is that if you compare an apple and a fire engine, right, the representation of red will naturally fall out, right? Of course, there are going to be other things that are in common, but if you do this enough times, if you compare apple and fire engine to enough other red things, right, eventually you get a fairly fine-grained representation of what it means to be red. And this process allows us to symbolize red from the distributed inputs, right? And that gives you the power to be able to think about red without having to activate or think about every red thing you've ever seen or every red thing you've ever learned anything from. And that ability to separate a useful, stable, symbolic representation from the statistics from which it was learned gives you a generative system. All right, so I'm going to, again, with my PowerPoint animations, try to illustrate this. So we have our nodes connected to our feature inputs. So this is a distributed representation. And we're just going to compare the two items that you encounter. There's going to be stuff that's the same and different. And because the activation function of the nodes is constant, we can actually use both sources of information. So we can use what's the same and what's different and grow or code another node on another level that says, okay, this is the thing that was the same in these cases, and another node that says, okay, these things were different. And if we compare them to enough cases, the code or the distributed pattern that this node responds to becomes very well defined to pick out things like red or shiny or edible or noun, right? So how we actually go from something like this to something as abstract as linguistic categories is much an open question, but it's the first time I've seen a way forward to learn that kind of information. So then just to try to summarize again what that is, it's learning invariance from experience, and it's learning it through what we call intersection discovery. So discovering the intersections of objects and then symbolizing them. And that is essentially learning a new data type, right? And that's what allows the system to become generative, right? It allows the system to then apply those data types, those symbols, to things it's never been trained on before. And this also allows it to have the important feature of value variable independence that means thinking about red without activating all the red things. Of course, now there are still problems. So everything I've described to you has been in a predicate logic, right? So it's not a natural language representation in the purest sense, and that's partly because we don't know what the right formal analysis is yet. We certainly need a probabilistic parsing element. But again, I don't think that's the whole story. That's what I meant when I said I don't think that the natural language processing parsers or the statistics like surprisal or others are enough to get us there, because those are still just statistics over representations. You have to have something to count, right? So we really need an account of how we got those representations. And then later, yes, counting them and seeing where they appear and what context they appear is very important. But first, we need the representation. Another problem that we face is how to cache out the feature space and the vector input. That's where a lot of the fancy footwork goes in deep learning models. So what's the information that you want the model to generalize from? One of the things we're looking at is to see if we can get the models to take ASR output and generalize it. That's something that's syllable-like or word-like, but that's a hard problem. And yes, of course, then here, although I say I don't worry so much about the isochrony issue, it would be nice to be able to do the same thing, but with natural speech data. All right, so I'll conclude. Basically, by using time or desynchronization across levels of representation, the model is able to represent symbols in a neural network. It can learn new data types from experience, which makes it more expressive. And this means that this subroutine, time-based binding as we call it, it's explanatory for these analogy tasks that I talked about, but it's also, beginning to edge in the right direction for sentence processing, I think. And that, I think, is an attractive feature, right? Because it's not coming up with a new mechanism, it's repurposing one. Right. And so I just want to say that in a sense that's telling you how we perceive hierarchy from a sequence, and that how, that mechanism, is what gives off the oscillations, right? It's that binding information in time. Okay, and now I'm going to interrupt the regularly scheduled programming for some infomercials. So here's some of the posters that are coming from Nijmegen here, and the first is from Hans-Rutger Bosker, who has some interesting behavioral data that answer some of the questions that were coming up earlier about whether we can see a rhythmic entrainment persisting and whether it shapes perception, and he finds that behaviorally it does. And Anna Kusum also has some compelling MEG data that speaks exactly to this issue. I think it's something that Joachim Gross was talking about, so that's a good thing to come see this poster about and talk to Anna about. And also Philip Alday and I are working on trying to use machine learning to figure out if there are kinds of linguistic representations that might be better encoded, in this case we mean better detectable, in one domain or another. And so far we've been using syllables, stress syllables, and canonical or well-formed lexical stress versus bad lexical stress, or something that's not the right stress for the word. And we found, surprisingly, that stress syllables, well, this is actually unsurprising, are really easy to detect in the time domain, but less easy to detect in the frequency domain. But what I think is most compelling and interesting is that detecting lexical access, or well-formedness in terms of lexical stress, is best detected in the frequency domain. And with the methods that Philip is developing, we're able to actually zoom in on the frequency bands that the algorithm is using to detect the pattern, right? So in a sense, yes, these are coefficient weights, but they're also hinting at how the brain might be encoding information at different frequencies as a function of linguistic representation. So it's a poster that Philip will present tomorrow. And then my PhD student, Greta Kaufeld, is trying to do the most ambitious thesis I've heard of yet, which is to generalize this approach across production and comprehension, right, to try to track contributions of the knowledge we have stored in symbol form as it's applied to the bottom-up speech input, and then also to do that during production. So good luck to her. We'd like your feedback, though. And that's it. So thank you very much for your attention.
Questions? Thanks a lot, Andreas.
So I want to go after the invariance thing, which is very ambitious and a worthwhile thing to pursue. How are you going to prevent from finding invariances you don't want to find?
Yeah,
so
that's one of the
what's
problems
the restrictive
if this
thing?
model is too generative. So there's a representational explosion. So we need to come up with some more either, neurobiological constraints or memory constraints or other human-motivated constraints to cap the representation. Okay. To cap the generative explosion that happens. And it's very much dependent on the kinds of things that you let it compare, right? So if you just let it go, it compares everything. But obviously, I don't think humans do that, right? We don't compare some new utterance of a word I heard, or as a child, some sentence that I heard with, the pattern on the floor. That's not how we learn stuff, right? But the model would do that. So we need a way to limit that. That's true.
But I mean, does searching for invariance come out of the box? Is that something as part of our cognitive architecture? Or is that something that actually is a consequence of the modeling you're doing? That is, I happen to be the kind of system that looks for invariance.
I think it actually...
alternative would be that that's something I do. My perceptual and cognitive systems are organized to find sameness rather than simply always search for difference.
Well, I want to say actually yes, but I think actually it comes from being an entity or a system that is extended in time and in an environment, right? So the fact that you have a state at time t, and you're going to have another state at time t plus 1, if you have any memory at all or any continuity of being, right, you can compare those two states. So at its most basic level, it just comes from that. But I also do believe that a lot of the subroutines that are giving us human-level cognition are indeed out to find patterns and generalize from them. So yes to both, I guess.
Lars?
Danke. I have two questions, so thanks for the very interesting talk. So the first one, why is this not a parser? I mean, isn't it a top-down
and
a left corner PCFG?
It doesn't store a bunch of representations and then search between them and be like, which one fits? It doesn't do that.
Okay.
But actually, as much as I'm being negative about parsers, I think we need to move closer in that direction, right? So the weakness there is like, what has it actually generalized, and how does it know when to activate that? So that needs to be more parser-like.
That's actually the next question that I have. So, can you derive hypotheses like with respect to the Ding data? Actually, I'm thinking of the Nelson paper and how John Hale kind of pitted left corner, right corner. So the amount of structure that's projected with any given word, right? And you were showing how like maybe a verb would project its whole verb argument frame and so on, and you can like fill the slots and so on. Could you, from that model, like find out in the Ding data when actually the phrase is projected?
Well, in our model, we have like, 9.
So in time, right?
Yeah, so it's more uniform. So it's on as long as that representation is on, and so that runs into the same problem we've been discussing. Is we don't know, when it's over, right? So if there's some kind of recurrency, that's the other thing that needs to be built into the network, right? That the phrase is on as long as there's some kind of recurrent sampling.
Yeah.
Then it can go off in a natural way.
So you say it wouldn't change the height of the bar and the bar plots that you showed. It would just stay the same no matter where in time it happened because...
So the other thing I think about, so when I was saying I don't worry about the isochronies, I think it's all relative anyway. So, yeah.
I liked it very much. And I have a question. When you say time, you actually win sequence.
Yes.
You don't care about time.
Well, we can do time multiple ways.
No, I know you can, but in the architecture, it's basically maintaining a sequence.
Yeah.
Okay.
Yeah.
And
Well, it's
then-
maintaining multiple sequences at multiple levels. So it could do it infinitely. And that's another way that we have to constrain it, is say, okay, there's only a number of bindings you can maintain. Otherwise, you will generate everything.
Which leads me to this question, if you would know where to concentrate the learning by segmentation, would it help?
Yeah. So, and the other interesting thing that I think about in context with this is that the way the model learns is that it takes a larger segment, and by comparing them, that's how it goes down and gets the lowest meaningful unit, or the lowest sort of unit that appears in other combinations, right? So it's a way that you think that would be a natural way to both segment speech in real time, but also to learn it, right? So how do you learn the part that you have to then detect later? By comparing lots and lots of arbitrary length things and then generalizing the bits out of it.
Hello. So thank you for the wonderful talk. So could you go back to the slide where you compared the representation of sentences and Jabberwocky sentences?
In Dora or in the...
I mean, some blue plot showing different nodes.
Oh, you mean the like crazy vector thing that's not very readable by humans? Sorry, I don't like clicking through slides.
Oh, yeah.
This one?
Yeah.
Yeah, okay.
So what are the nodes here? I mean, are they the nodes for the phrases, sentences, or for the features?
No, so this is in the long-term memory, so not in the driver or the processing buffer where processing is happening. So in the driver where you're actually binding stuff together, Jabberwocky and grammatical look identical, because it's learned that these are the kinds of things that we bind together, so it's binding them together. But then if we allow it to try to make contact with long-term memory and form new representations, it distributes that information differently. So the stuff that it's seen before, in this case we call that grammatical, that's also a sleight of hand in a way, the activation is more peaked. So what this is for every 10 cycles, so for every 10 sentences, we average that activation together. Otherwise it would be just even more pixelated and so harder to see with our visual system. But so for every 10 cycles, we average the activation across long-term memory, and the darker blue something is, the more activation is focused in a particular node. So these are all the nodes, right? So that means that combinations of predicates and arguments that it's seen before are more highly recruited in the grammatical case. The activation in memory is more widely distributed in the Jabberwocky case, even though it is binding the words and phrases together into a sentence.
Cool, thank you.
So just following up on Nai's question, maybe this is something I didn't understand, but what would make the Jabberwocky not grammatical? How would the system know that? So we know that these are not grammatical sentences.
Well, so it doesn't know anything, right? It's just a bunch of numbers. But what it's doing here is we've given it the grammatical stuff and let it generalize from that first, as a sense of saying, this is your language, right? These are the combinations you know. but it's extracted something about the pattern, probably because the structure of these is all identical, that it recognizes or activates in the Jabberwocky case that's not present in the word list and the noun phrase case. And it can still form those representations, but in its memory, those representations make less contact with existing ones because it hadn't been trained on them before, right?
Right.
But
So-
if it got more of them, it would generate representations like the Jabberwocky.
Right.
So it doesn't have a notion of grammatical order.
But if you gave another set of grammatical stimuli that it hadn't seen before, would it be the same as the Jabberwocky, or would there be a difference?
That's a good question. So I think actually in this case, I would say it would probably be like the Jabberwocky.
Okay, so you would need an extra element to sort of get to the essence
Well, so
of
another
what
way to say
makes them
it,
grammatical
another way
or
to
not.
say it is that from here it's generalized something that's, I don't want to call it syntax, but it's syntactic, but no, it has not generalized semantic composition. And probably I think it would need other sources of cues in order to do that.
Okay. And another question about
It would
time.
need a corpus probably. What?
And another question about time.
Yeah.
Which was, if I understand correctly, the way the model works is that for some words it knows that it needs to wait a certain amount of time in order to be resolved.
It's not waiting. It keeps a level of act. So it
Right.
It
It
has
keeps
a,
it, yeah, it keeps a
it
level
has
of
a
activation
conjunctive
until
code.
resolution.
So the activation function is continuous, so it's not a threshold function. So it doesn't have like they're not spiking units. They're just units that have a continuous activation function.
Right. So how does the model know how long it has to stay on, say, for example, for fun and for waste?
So
That's
that
what I
is
mean.
learned. So that's learned from
Right.
the stimuli. So that comes from the stimulus presentation rate, and the fact that it's learned these one-place predicates.
Right. So again, generalizing to broader language, say for waste, you need to wait for its
so it
resolution,
kno-
but
so
it
the-
could
right.
be in different sentences. You might need to wait 1 or 2
Yeah.
or
So
5
so again,
words.
remember, it only represents two-place predicates, and so that's equivalent of saying what it says is fun games, waster, time, wasty, right? That's not how we speak.
Right.
So, but the reason why it represents waste in that sort of asynchronous way is because that's how it represents two-place predicates. Because it's another hierarchy of that asynchrony. So it just does it on another level. So, and that is all driven by the 4 Hertz presentation, right? So it keeps it on for twice the time because it needs to bind 2 units, and 4 times the time because, yeah.
And I think this speaks to the question of, is the isochrony here, right? It's a byproduct of the stimuli, so therefore we know that there's X number of units
Sure,
to wait,
but
but if you would want to generalize it to the hierarchical system, it wouldn't actually know how long it would need to wait.
Well, so here's, let's do a nice thought experiment, which I love because I can just argue. So if you had a corpus, right, and somehow you knew what the right representation of all the levels of linguistic analysis were in that corpus, and you had the model generalized from it, it would be able to know things like two-place predicates or argument structure or thematic roles or subcategorization information,
You could
which
open
at
up
least make
prediction
predictions about how many arguments or how many constituents might occur. Those don't have, right now, it's determinate, but it doesn't have to be that way. So, yeah. But the isochrony is not, here, it's useful for the example, but it's not necessary. It's the relative timing, it's the desynchronization across layers that does it.
Last question.
And that's a shame. I think this is a bad question.
No, there's no such thing as a bad question.
Well, let me try.
Okay, I like it. I like it already.
I think so. Part of what you showed was that with a simple RNN, you can't reproduce the ding data. And
No,
I think,
I can't reproduce it.
well,
Yeah.
you can't represent. You can't get the interesting parts.
Yeah.
I think at CUNY, Stefan Frank claimed
Oh, yeah.
that he can not only get an RNN to do that.
No, so what he claims, actually, which is, you might find this more interesting or not, I don't know, he can vectorize the
Yes.
data, so you don't even need an RNN.
Yeah, he just convolves it
But
with
this is,
random noise.
for me, this is all the same deep learning tricks, right? So if I put lots of second order, third order statistics in my vector, yeah, I can perform a lot better. But that's not the same thing as, do you really think that, like, in speech, children are extracting multi-level vectors of, like, I don't even know what that's just, I don't even know what units that would be represented in. But yes, because of the isochrony, right, he can get some periodicity, but it's not, yeah, it's just, I don't know, for me it's a signal processing trick, but.
Well, I'm not, so word2vec is not a deep model. It has one layer, and it's a pretty stupid layer.
No, what I'm saying is that the input, the way that he vectorizes the input is a lot how training data sets have to be made for deep systems to be able to learn. So for example, we're working on this simulation of singing happy birthday with the idea that Dora can sing happy birthday in any key that you give it once it learns the relations. And we have a deep network, and what it does is it just, the more layers you add, the more the sound gets decomposed into like non-pitched tones, like not a tone, not a pitch, just noise. Because it's learning, that's why it's great for biomedical imaging. It's learning these statistics that are so, you know, I hate to use the word abstracted because it's one of my favorite words. They're so abstracted from the input that that's how it's generating the performance. But sorry, I'm hijacking your question. Go ahead.
No, it's okay. I said it was a bad one. Thank you for answering it in a not so bad way.
Thanks again, Andrea.
Thank you.
It was a great talk.